In this example, we're going to use the equivalent lateral force analysis method to expand on a problem that we looked at previously for a site in the St. Louis, Missouri area. In this example, we're asked to determine the lateral seismic loads on the idealized shear frame shown here using the equivalent lateral force analysis method. The site is a site in the St. Louis, Missouri area with a soil characterized by a standard penetration number of N equal to 25. The lateral force on each level, F sub x, is determined as a product of C sub Vx times the base shear, V base. C sub Vx is the vertical distribution factor that's based on the equivalent lateral force analysis, and the base shear, V sub B, or V base in this case, is calculated as the product of C sub S times W. C sub S is the seismic response coefficient, and W is the seismic weight for a structure. This structure is rather simple, so the seismic weight can be determined as the sum of the weights at the individual levels, and we have W equal to 1,360 kips. Before we can determine C sub S, the seismic response coefficient, we need to know what the approximate fundamental period of the structure is. For this case, we'll use T sub A equal to C sub T times H sub N to the X power from section 12.8.2 of the 2016 edition of the ASCE 7 standard. And for a steel moment resisting frame, we would take C sub T equal to 0.028 and X equal to 0.80. And for this moment resisting frame with a height of 70 feet, we would get an approximate fundamental period of 0.838 seconds. Alternatively, we could use T sub A equal to the number of stories divided by 10, or 0.1 times N, and get an approximate period of 0.5 seconds. In this case, we'll use the first form, and we'll move forward with a value of T equal to 0.838 seconds. To determine the seismic response coefficient, we first check the peak of our response spectrum by dividing S sub ds by R over I. R is response modification factor, and I is the importance factor for earthquakes. In this case, we have an S sub ds value of 0.434 times G. R is equal to 3.5 for the moment resisting frame, and I sub E is equal to 1.25, which indicates that this must be a risk category 3 structure. So in this case, C sub S would have a default value of 0.155, which would be indicative of the peak of our seismic response spectrum. However, C sub S should not exceed either S sub D1 divided by T times R over I if our period of our structure is less than T sub L, and C sub S should not exceed S sub D1 times T sub L divided by T squared times R over I if the period of our structure is greater than TL. In this case, the period of our structure is equal to 0.838 seconds, which is less than TL, so the first of those two equations, equation 12.8-3, applies. Substituting in, we see that C sub S need not exceed 0.243 divided by 0.838 times R over I equal to 3.5 divided by 1.25, or 0.1036. So this indicates that the period of our structure is greater than T sub S, and we have the seismic response coefficient equal to 0.1036. However, we have minimum values of C sub S that need to be checked as well. In this case, C sub S shall not be less than 0.044 times S sub ds times I. That would work out to be 0.02492. And in addition, for structures where S sub 1 is greater than 0.6 G, C sub S shall not be less than 0.5 S sub 1 divided by R over I. That doesn't apply in this case. Since that doesn't apply in this case, then we use C sub S equal to 0.1036, and we have a base shear, V sub base, equal to 0.1036 times our seismic weight of 1,360 kips, equal to 140.9 kips. Now that we have the base shear for our structure, the next step is to determine the vertical distribution of forces. This is the determination of the forces that are applied at each structural level in our structure. And in that case, F sub x, the force at each level, is equal to C sub Vx times the base shear. C sub Vx is determined using this equation, where we have the weight at each story times the height of that story above the ground to the kth power, divided by the summation of W times H sub x to the kth power. This is equation 12.8-12 out of the 2016 edition of the ASCE 7 standard. We need to determine the value k first, so since t in this case is between 0.5 and 2.5 seconds, we interpolate to find k. And in this case, k would be equal to 1.169 seconds. So if we consider the fourth floor as an example, the weight of the fourth floor is 300 kips. The height of the fourth floor above the ground level is 42 feet. So we can calculate W sub x times H sub x to the kth power is equal to 23,697. We can do that for the other remaining levels in the structure. And if we take the summation of all of those values, we find that the summation of W sub x times H sub x to the kth power is 101,144. Next, we can calculate C sub Vx, the vertical distribution factor for each of the floors. Using the fourth story, or the fourth floor, again as an example, C sub V for the fourth floor would be equal to 23,697 divided by 101,144. Or C sub V for the fourth level would be 0.2343. Doing that for each of the levels within the structure, we can then calculate the forces for each of the levels in the structure by multiplying C sub V for the level times the weight at that level. For example, for the fourth floor, we would calculate the force as 0.2343 times 300 kips, or 33.01 kips. So for all of the stories together, you can see that we have these values for the forces F sub x. Note that the sum of these forces should equal the base shear that we determined earlier, and in this case, within the precision that we're working, we find that that is true. So finally, these are the story forces that would be applied to our structure for our analysis. So the next step would be to do an analysis of that structure, determine the bending moments and the shear forces in our beams and our columns, and then determine appropriate sizes for those members to resist those forces.